In this video we begin a discussion of the electronic structure of multielectronic atoms. Okay, so in the prior videos we have seen how to solve the Schrodinger equation for the hydrogen atom or hydrogenic atoms that only have one electron. But of course most of the atoms in the periodic table have more than one electron, and the question is how do we describe what the electrons are doing in those multielectronic atoms. Well, much as with anything else, what you would like to do is set up the Schrodinger equation for that particular atom and solve it and see what the energy and wave function solutions look like. Alright, so we're going to try to do that for the helium atom, and we're going to see what are the challenges that emerge from doing that. Alright, so the helium atom is going to have now 2 protons in the nucleus and then 2 electrons in the periphery, which are going to have some wave behavior. Right, so to try to set up the Schrodinger equation for that system, what we would do is just write that expression and then think about the Hamiltonian operator. Hamiltonian operator is going to have 2 terms, as always. It's going to have a kinetic energy term and then a potential energy term. Now the kinetic energy term now has to take into consideration the motions of 2 electrons. Okay, so you will have the expression is going to be equal to 2 terms that depend on the second derivatives with respect to the motion of each one of the electrons with respect to each one of the axes. Okay, so this gets a little bit complicated, but it's just a straightforward enhancement to what we know for the hydrogen atom. Now, what is very interesting is what happens to the potential energy term. Okay, the potential energy term, you have to figure out what are the interactions that are taking places between all of the particles that you have in your system. Okay, so the first thing that you can have to think about is that, again, you're going to have 2 electrons, and the first type of interactions that you will have is the attraction between the nucleus, which has a nuclear charge now of 2, okay, with electron 1, and we can write that simply as this. And then you have the attraction of the nucleus with electron 2, which will be written as this. Alright, and R1 and R2 are simply the distances of those electrons to the nucleus. But then you also have a new term, which will be the repulsion between the electrons. Okay, it has a positive sign that means a repulsion, and then this will be written as this. Okay, this is R12, that will be the separation between the 2 electrons. Well, it turns out that the presence of this term right here, the term that is responsible for the interaction among the electrons, that already makes this expression impossible to solve analytically. Okay, so it cannot be solved exactly. Instead, what people do, or what we do, is try to solve it approximately, and then try to see if we can learn something from those approximations. Okay, so a typical approximation that is used is to assume that the wave function of this helium atom, which has 2 electrons, is going to be just the product of the wave function if the electrons were independent. Okay, so that will be simply the wave function of electron 1, okay, multiplied by the wave function of electron 2. This is called the orbital approximation, and this is exactly what we do when we talk about electronic configurations, which we're going to see. Okay, so for the helium atom, what we will actually say is that the overall wave function, electronic wave function of the helium atom, is just going to be the wave function of the first electron multiplied by the wave function of the second electron. Okay, so the question is, well, how are those wave functions? It turns out that with those approximate calculations, we can actually see that these wave functions are exactly identical, or very similar, to the ones that we actually have in the hydrogen atom. Right? So these wave functions here for the independent electrons are still going to be what we call the 1s, 2p, 3d, and so forth wave functions. Okay? So then the question is, well, how can we describe then the helium atom in the lowest energy state? Okay? Alright, so before we actually do that, we have to incorporate something that is called the electronic spin. Okay, so when we were talking about the hydrogen atom, we said that the wave function of the hydrogen atom can be characterized by just 3 quantum numbers, which we called n, l, and m sub l, and we talked about those at length. Okay, now it turns out that there's a 4th quantum number, which is not necessary to explain the quantum mechanics of systems with just 1 electron, but is there. Okay, and that is the spin quantum number, which are going to be called m sub s. Okay, so in reality, every single electron has 4 quantum numbers, and again, even though when you have only one electron in the hydrogen atom, you only need 3 to specify what the motion of that electron is. Okay, so what is the spin quantum number? Spin is an intrinsic property of fundamental particles, right? And it does not have a macroscopic analog. Okay, so that makes it very difficult to explain. However, the model that people use to explain what quantum spin is that for electron, for example, you can assume that that electron is going to be spinning about itself. And again, this is just a model because we don't really know how this motion really is. And then, because that motion is quantized, in the case of an electron, you can only have 2 types of motion. When this electron is spinning about itself, right, so you'll have your nucleus, and the electron is spinning about the nucleus, but the electron is also spinning about itself. That's what we call electronic spin. And it turns out that electronic spin is quantized. So you can only have 2 types of motion, which you want to call up or down. Or we can say it's clockwise or counterclockwise, right? Those are the only 2 possibilities. And we can distinguish those by making the quantum number simply being equal to +1/2 or -1/2. Okay? So again, we just learned that in order to fully characterize an electron, you actually need 4 quantum numbers, not 3. The 4th one is the electronic spin. Okay? Or the quantum number that characterizes electronic spin. Why is this related to the electronic structure of the helium atom? Well, it is related because it turns out that 2 electrons can have the same wave function, the same orbital, as long as they have different spins. Okay? So when we're trying to answer the question, well, what is the electron configuration of helium? Okay, notice that when you think about the lowest energy state, okay, of helium, this is energy. The first wave function that you have of lowest energy is equal to the 1s orbital. Okay, then you have the 2s, 2p's, and then those orbitals have higher energy. Well, it turns out that, again, this 1s only gives you the values of n, l, and n sub l, 1, 0, and 0. Right? So for the helium atom, what we'll actually say is that, well, it turns out that the 2 electrons that you have in the helium atom can have the same wave function, 1s, can have a 1s orbital, as long as their spins are antiparallel. Okay, and that means that the quantum numbers, the spin quantum numbers have to be different. Right, so for the helium atom, the first electron, we can say that it has quantum numbers 1, 0, 0, +1/2. And then the second electron will have quantum numbers 1, 0, 0, then -1/2. Okay? Right, so this is how we describe electronic structure of multi-electronic atoms. You have to look at every single electron and then describe what the wave function of that electron is. Okay? The lowest energy structure in the case of the helium atom is that in which one of the electrons has these quantum numbers, the other electron has these quantum numbers. The language that we normally use to explain this is to say that, well, the 2 electrons in the hydrogen atom, in the helium atom, occupy the 1s orbital, okay, and as long as they have antiparallel spins. Okay, this antiparallel spin here is what we call the Pauli exclusion principle, again, which says that you can have the same 3 quantum numbers n, l, and n sub l as long as you have opposite spins. Right, so again, this gives rise to what we call the electronic configuration. Okay, in general, the way that we actually do this is to say as follows. What is the lowest energy configuration of helium? This is just 1s2. Okay, but this means much more than that. Okay, what this means is that we can describe the overall electronic wave function of the electron as follows. The first electron, okay, can be described with a wave function which is the same as the 1s orbital in the case of the hydrogen atom. And it has a spin +1/2. The second electron can be described by the same wave function, 1s, but it must have an opposite spin, in this case -1/2. Okay, and the overall electronic wave function then is going to be the product of those 2. That will be what we call the orbital approximation. Okay, so again, in general, we're not going to be going through all of this detail. Simply when you actually write the electronic configuration, you just write this, 1s2. And the language that we use is that 2 electrons occupy 1 orbital with antiparallel spins. But again, you can see that that is actually much more nuanced than we have made it out to be in earlier courses like in our chemistry, in which we simply write electronic configuration as 1s2. Okay? In the next video, we're actually going to continue to talk about electronic configuration of multi-electronic atoms by looking at lithium and so forth, going down the periodic table.